A block of mass m slides along a smooth curved bridge surface which forms a circular arc with radius r. On the left side of this bridge, there's a point A exists. And the block moves with a linear speed v at the point A. The line connecting point A and the center of the circle forms an angle theta with the vertical. This is angle theta, and this is a vertical line. Part A. 1. Draw the free body diagram of the block at point A. 2. Determine the magnitude of the centripetal force acting on the block at point A. 3. Calculate the normal force exerted on the block at point A. First, let's draw a free body diagram. It's supposed to be free for you, right? If you don't know how to do it, go study harder. So first, let's draw a center of mass of the object. Obviously, there's gravitational force that act on it. This is Fg. And there's obviously normal force. However, we have to determine what's the direction of the normal force. So at point A, the plane that the block contact with is actually tangent to the circle at point A. What it means is, at point A, the object is actually contacting with this surface. And it is tangent to the circle. Using geometry, we can get this is actually 90 degrees, right? And it's one speciality of the normal force, which is always perpendicular to the surface that it is contacting with. So the normal force is like perpendicular to the surface it's contacting with, right? So it's supposed to be to that direction, 90 degrees. So let's draw it. A 90 degrees around that. So that's the direction of Fn. On the test, you may probably mark that this angle is theta to make it like clear to your teacher that you understand how the direction of normal force is being determined. However, over here, we don't need to do that. And over here, you can suddenly realize that, oh my, 90 degrees, 90 degrees, one line, which we can prove that the normal force, the segment line AO, are actually on the same line. Or the normal force is collinear with the radius of the circle corresponding to point A. That's very, very important. However, it's not that important in the second part though. On the second part, determine the magnitude of the centripetal force acting on the block at point A. What is the formula for the centripetal force? It is just Fc, right? Is equal to MAC. What is the formula for AC? V squared over R, right? When we plug it in, it will be M times V squared over R. And let's see which value we should replace with the value that we already know, or the variables we already know. Do we know V? Yes, we do. Do we know the instantaneous velocity of the block at point A? Yes, we do. Do we know the radius of the circle or the path? Yes, we do. So that is your final answer for second part. Let's do the third part. I'll make this a little bit to the left. Calculate the normal force exerted on a block at point A. From part A, we already proved that the normal force is collinear with the radius of the circle corresponding to point A, right? So I should create another free body diagram real quick, because on the test you're supposed not to mark on your original free body diagram, because you should not, the components of the force should not be appeared on the free body diagram. So we're trying to find a centripetal force, right? What is the direction of centripetal force? Always pointing towards the center of the circle, right? So it's supposed to be pointing that way. And it is collinear with the normal force. Well, I already explained it before, so you might probably understand it. You'll probably understand it. So let's just separate them to component. Because we're trying to find a centripetal force, so we're like separating them into this direction instead of just regular vertical and horizontal component direction. So what components are on the line off towards the center of the circle? Obviously, 1 and 2. Also, we can get the angle, one of the angle which is over here is theta. So now let's write the expression of the centripetal force, or the net force, towards the circle, which will be net force is equal to half g times cosine theta using trig. Minus Fn is equal to mv squared over r. It's equal to centripetal force. Is equal to mv squared over r. Which we can get the magnitude of Fn will be Fg cosine theta minus mv squared over r. What is Fg? It's equal to mg, right? So the Fn, the expression for Fn will just be mg cosine theta minus mv squared over r. I'll make it look a little bit better. So it will just simply be m times g cosine theta minus v squared over r. So that is your expression for the normal. Alright, now part B. At the topmost point of the circular arc, the block may lose contact with a bridge if the speed exceeds a certain value. Determine the maximum speed a block can have at the top in order to maintain contact with the bridge surface. 2. If the bridge surface is not frictionless, does this affect the maximum speed of the block at the top of the circular arc? Explain your reasoning. First, the top point is over here, right? So let's draw a feedback diagram. I already draw it for you. So when it loses contact, right, the normal force will no longer exist. The only force that is collinear to this radius over here will only be Fg. So the only component of the circular force, centripetal force, is Fg. So let's write it down. It's pretty easy. The sigma F, the sum of F, is equal to Fg. Only Fg. And it's equal to Fc. And it's equal to m times v squared over r. What is Fg? It's equal to mg, right? Alright, we can only look at this part and we're trying to find v, right? So we can easily get v is equal to square root of r times g. That is your answer for the first part. Very, very easy, right? Second part is also easy. Trust. On the second part, if the bridge surface is not frictionless, so now we got friction. Does this affect the maximum speed of the block at the top of the circular arc? Explain. So if it's on the top of the surface, right? The surface it is contacting with instantaneously will be the horizontal surface. This will be the surface it is contacting with. So it's basically like the object is like moving on this surface at this instant. So over here, obviously the friction is like opposing its direction of moving. At this moment, the instantaneous speed and the direction of its moving is also tangent to the circle at the topmost point of the circle. So this is the direction, right? It's moving. It is moving instantaneously. So this will be the direction of the friction. You can obviously see that the friction force is actually perpendicular to the direction of the centripetal force. So there will be no components contributing to the centripetal force. So FF will not affect, will be no effect at all. So we can just write no effect. The reason you can just say that since FF is perpendicular to the mm, to the centripetal force direction, or to the direction. Well, let's write the line of direction of centripetal force. So there will be so so the friction force will be will have no effect. Have no contribution to the centripetal force. And if Fc stays the same, Fc is equal to mv squared over r, right? M doesn't change. We can just write delta m equals 0, delta r equals 0. That means it doesn't change. So we can get v will not change as well. That's your answer. So over here, the maximum speed of the object can have, it's with the friction on the surface, it's actually equal to square root of rg. So not change. One thing I need to mention is that when I'm recording the videos, I was trying to aim for efficiency, so the answer over here is not perfect. However, it is sufficient for you to get full points on the exam. If you want a complete and detailed solution, I'll include links to the answer document and the original question document in the description down below. Please check them out. Thanks. Without further ado, let's continue to our last FRQ.